So in Java, exception handling is a concept that happens in, well, all programming languages. Java just implements it. Very similar to other languages, so we'll look at the way Java implements it here. But the idea of what is an exception. So an exception would be, you have some code that's running, it performs some task, maybe like it's taking two numbers and dividing one by the other, and you're counting on the denominator of the number to not be zero. If it's zero, you're going to not be able to execute that line of code. Or example might be you go to open up a file because you need to read from the file to then create an email you're going to send out to all your customers, and the file you go to open is not there. Maybe the file gets created every night, and in the morning you have code that wakes up and opens it, and one day it's not there. So you can't proceed, or can you proceed? Could you proceed? So for example, suppose we had code like this. We have some code that reads a file, and we have a character set. We open up a file, we say it's going to be like US ASCII code. We go to open up the file's name is input.txt, and it's understood to be ASCII code. Once we open it, once we successfully open it, we then start reading the lines of the code and print them out. So the question is, what should happen if the input.txt file is not there in whatever folder you're expecting it to be there? What if it's not there? Or what if it is there but it has corrupted data in it? It's a JPEG, not a TXT file, something you can't read from. So if something unexpected happens, should your program continue? So this line right here, we're reading the file. The file's not there. The next line of code assumes now we have successfully read the file. So we make line equal no, and then we keep reading from the file. As long as it's not null, we keep printing out the line. But there's not going to be any line because the file's not there. Would this cause damage to run this code? Would the compiler, if you knew it at compile time, would the compiler know that this file may not be there? And could the code that's after the event, the exception, the unexpected event that happened, could the code after that, is it safe for the operating system to let it run? Just go, oh, I know the file's not there, no problem, I'm just going to let this code run. So would you let the code run, the code that appears after the exception happened? Would you, if you were designing an operating system, would you let that always run? And why or why not? You could say it.
What do you need that to be correct in order for the program to run the correct way?
Right, so like for example, if it was maybe creating some news article and now you're going to post it on your news website, now there'll be nothing there, that would look embarrassing. But maybe, like in this case, this is just reading a file and printing out results. If nothing comes out, maybe you're okay with that. So it's debatable, but from the operating system's point of view, the operating system isn't in your head, the programmer. Should it just let it go? Anytime an exception occurs, should it just let the next lines go? Or should it kick your program out? Or maybe should it be designed to give you the option? What do you want to do with this problem? Do you want to continue? Do you want to get terminated? So let it be your call. So if you were designing an operating system, how would you design it? That it would.
I said I would let the person choose whether they wanted to run it or not, because it may be something that's not important.
Okay.
Or it could be
Something that
destroys the entire program.
Right. Or it could be something like in this case, maybe we have like a backup input.txt file, like a default one. And if this one is not here, then maybe we could replace it with the default one and then pick up where we left it. Or you may want to do some cleanup stuff. You may want to broadcast out to your users, hey, we didn't get today's news feed, and then let it terminate. So you may want to perform some tasks and then still let it terminate. So the way the design of the operating system, we'd like to be able to say anytime a program is running, we'd like to be able to say, in the event of an exception coming up, here's the way the operating system will handle what to do with it. And the operating system, since it doesn't know your code, probably does some kind of cleanup and then eventually removes your program from the database, from the operating system. And the other thing is, when the code that's part of the operating system runs, it's kind of like an implicit call from your program where your code went bad, where your code hit the exception. It's kind of like when you go and you read an input file that's not there, this line of code is now going to generate a call to the operating system. A function of the operating system is going to go, okay, I know how to handle file not found issues, and I have some code that's going to run. I'm going to run that code, and then it'll terminate your program. But I'm not going to, when I finish, I'm not going to come back here like as if it was a method call that finished and came back and pick up where it left off. I'm going to implicitly call some function, an exception handler supplied by the operating system. I'm going to call it, and when it finishes, I'm not coming back, I'm going to remove you from the program. I could come back if I was instructed to come back, but the operating system will probably write it so that it doesn't do that. So, most programming languages that allow the programmer to interact with the operating system allows us to do something like, and in C++ and C# and Java, the format is almost the same across all languages. If you have some code that you believe from time to time may not run correctly, so you kind of think it may work or it may not work, we can have an open paren, closed paren block and put the word try in front of it. So any code that appears here, it's kind of like you're saying, I anticipate there may be an exception. Not always, but there may be an exception. So as this code is running, I anticipate that the file I'm looking for may not be there. So maybe I'm just kind of making it like in a variable now to show that the compiler can't even anticipate, couldn't even see the name at compile time to know if it's there or not. So I may not be able to open the file, but I'd like the code to run. And then if I hit a problem where the file's not open, I want to have my own code to handle that issue. I can do, whatever I want to do with it. So the question then becomes, what is the mechanism for us to be able to handle exceptions that are coming? So we have three different types of exceptions. There's checked exceptions. Those are the ones where the user can anticipate them. So an example would be like a file not found error. There are error exceptions that are external to the application, something like a phone overheating. Couldn't have software come up or even see that one coming. And then there's ones that happen at runtime errors. So if you're running and you happen to do a divide by 0. So something like that can happen. So yeah, some interesting questions show up in the flow of control. Your program's running, your program hits an exception, an unexpected event occurs. So should the operating system just always kick your program out? Should you be able to decide what to do with that code, with the code that follows it? Should you be allowed to let it continue? Should you have an opportunity to make some adjustments, and then you decide if it should continue or not? So really, what should happen in the event of an exception happening? So the design of the operating system is going to be when your process is running, the operating system is actually going to have many exception handlers for different types of problems that could come up with your program. And if that problem happens, implicitly, the code that handles those problems will get called. We will get called. And the question is, when this code finishes, if you think of it like calling a method, when you call a method, you run down the code. When you get to the bottom, you return to who it called from and continue from there. In this case, we may not want to do that. Just because the operating system noticed that the file was not found and prints out a message, you have a file not found error, doesn't mean we want to go back to the code and pick up where it left off. But we would like to have the option to go back to the code and pick up where it left off. So the way the operating system is going to organize this, it's going to build a stack of problems that could possibly happen. And you'll see the kind of the I don't know, the genius of this in a second. When any exception occurs, we go to the top of the stack, so it's sometimes referred to as the operating system is throwing the exception. We're throwing the exception into the top of the stack, and then the top of the stack, so different types of errors that could happen. We go down the stack and say, is this the type of the event that just occurred? And if not, you go to the next one. If this one is, or if it's not, you go to the next one. And then you say, okay, here, it's interrupt number 28. Let's say the operating system has interrupt number 28. So then we say, okay, the code is here. Now the code here starts running like almost as if it was a method call. But it's not an explicit method call. You didn't call the method. You had an exception. The operating system saw the type of the exception, created a Java object, which is a type exception, and threw the exception into the stack and found a match. Said, here's the code. Now, if this code runs, does some kind of, the operating system is saying that, your problem is this, and here's how I'm going to try to clean it up. What would run right after this exception handler finished? Where would control now go if you were designing the system?
Right to the thing that, right to the thing after the exception happened. Like, the reason I went to the exception.
To go
You go back to your program.
Go back to your program, like as if it was a method call.
Yes.
Well, okay. The ones that are supplied by the operating system, they don't know if your program can continue. They might not want to do that, but maybe you might want to do that. So in other words, what we'd like to do is provide a mechanism where you can put interrupt handlers on top of the stack the operating system gave you. Add more stuff to the top of the stack. So if an interrupt that you expect to happen comes up, you have handlers at the top of the stack, so it will be a match and it'll run to your code. And then your code could decide to go back to where it left off or not. So an operating system handler, I just said, let's say handler number 28. If this code ran, now all of a sudden everything above the stack has been popped off. This code ran, it's probably not, the operating system is probably not going to go back to your code because it doesn't know your code well enough to know that it can go back to it and safely run. So would it just end right here, or at the very, very bottom of the stack, in the Linux system is a method called terminate, which just cleans your program out of the system. It will take the exception handler that was thrown into the stack, and it will rethrow it into the stack and go down further and further, looking for other matching, maybe more vague error handlers to run, and work its way down to the bottom of the stack, and finally you'll be finished. So if you write code and you anticipate, in my code, so you're writing your code, and then you're saying, in the event of a file not found, here's what I'd like to do. And also in the event of a divide by zero, maybe you anticipate a couple of things could go wrong. You would like to stack error handlers on top of the stack that the operating system gave you. So the way, like I said before, the way we can do this is by saying from this point to this point, I'm going to try this code, put this exception handler on the stack, add it on top of the stack. And then if it's done, once this thing is finished, it will come back where it came off to, unless we specifically say take the exception and rethrow it back into the stack for further handling. So we could have, for example, now the way Java does this is it has objects of type exception. So Java creates objects of type exception. You create that object, and you throw that object at the exception stack. So Java has a class called arithmetic exception. And in there, there's a bunch of methods. One of the methods I just decided to use as an illustration is a toString method. So it'll take whatever your exception is, convert it into a string so you can print it out and see what the problem is. And they usually take an instance of the object that you have. It says, what type is it? And then it basically says, you know, what is the message? What is the exception? What is the problem that you have? So if you wanted to see what it was, you would call the toString method and then have that print out what the method was. You could come along and add new exceptions. You could make up your own underflow exception, which extends arithmetic exception. So you would inherit these methods. Divide by zero, zero divide exception, which extends arithmetic exception. Overflow, which extends arithmetic exception. And if you wanted to, you could overwrite any method that you inherited. And you could say, you know, there's no problem here. You could decide that overflow exceptions to you are not a problem. And then, if an overflow exception object was created during the running of your program, you had an overflow, right? You had two 32-bit numbers together and you get a 33-bit number, and they can't store it. If you put this in, and then put this on top of the stack, an overflow exception object would be created. This code would be found to match, this code would run, and then it doesn't rethrow back to the stack, so your code would pick up where it left off. And it would even, you know, print out a no problem here now. So if you had this hierarchy, and then you went and you put some code here, some math-related code, and now we said I want to catch a series of exceptions. So I'm basically adding, on top of the exception stack, I'm adding a new set of problems that may happen. So I have the overflow exception on the very, very top of the stack. So it would be kind of like, you're not putting this on top of the stack and then this on top of this and then this on top of this. It's actually like you're cutting and pasting what your catch clauses and putting them as is on top of the stack. So the very top of your stack would be the overflow exception, then below that would be the arithmetic exception, which is this is a subclass of this. And then below that we'd have like a divide by zero issue. So in this particular case, yeah, I even have a comment up here. This would be kind of poor programming because you put a divide by zero below an arithmetic operation. So any object that is of type divide by zero, because it inherits from arithmetic operation, is also an arithmetic operation. So if you hit a divide by zero problem, it would say, is this divide by zero? No, it's not. Pop that off the stack. Is this a divide by zero? And the answer is yes, because it inherits from here. So this handler would run. And then this one would pop off the stack unless you threw it back, you threw the divide by zero object back here. This would never run, because this one is sitting on top of it on the stack. So you probably want the more specific problems at the top of the stack and the more vague ones at the bottom, in general. Okay. So yeah, so in Java we have, the base class of all Java objects is object. Then there's a class called throwable. So these are things that can be thrown, and there's two types. There's errors and exceptions. And then the class exception inherits or extends from throwable. And then runtime exceptions extend exceptions, and then like arithmetic exceptions extend from runtime exceptions. So you can go and create these objects as needed. And then there's also the idea of what's called a stack trace. So if you suppose you have a program A, which calls program B, and method A calls method B calls method C calls method D, and method D has an exception. Your stack trace would be which method called which method, which called which one to finally hit this problem. So you'd have, you could use that for debugging reasons. Maybe the way method D was called by C is a problem. Or maybe only the way B calls C causes this problem. So you'd have a stack trace. And you might get, I don't know if you've ever gotten error messages like this when when a program fails? It's, oh, yeah? Okay. But do you ever get something like this come out? Like you have an error and you get a stack trace like this? Okay, so it's just basically saying in what line of what, method called which one, and so on, and what exception you may have hit. Okay. So now there's the idea of if you put an error handle on top of this exception stack, and an issue occurs, and it goes down the stack and finds your error handler handles the code, it's going to then come back to wherever the implicit call to the error handler was. If you wanted to keep going down the stack further and further, you would want to put in code that says throw an exception. So what you could do is, for example, we could intentionally throw an exception. We could write code that says, even though no exception happened, I'm going to now create an exception object and throw it at the stack. So you're kind of explicitly, implicitly creating an exception. So we could have a method called divide. Maybe we're going to divide x by y. And we could say, if y equals 0, let's say y is going to be the denominator, we can throw and create a new divide by 0 exception and just throw it at the stack. So instead of us implicitly running this line, divide x by y, and all of a sudden hit a problem, what we're going to do is actually, so this really doesn't help anything, but what we're going to actually do is say if y is 0, which means it would have caused a divide by 0 error, we'll create a divide by 0 object and then just throw it at the stack. So it'll be like as if a divide by 0 happened here. So this is where we're kind of doing it intentionally. So now we could say try, call the divide method, divide 12 by 0, and then catch a divide by 0 error. Divide by 0 exception, because we could create our own objects if we want to. And then print out, oh, we had a divide by 0 error. And then we could just keep moving right along. If we wanted to, after the divide by 0 error message printed out, if we wanted to rethrow it at the stacks to get our program cleaned out, we could. We could just throw it again at the stack. Okay. So then there's the idea of you can throw an exception or you can create a new exception and throw that too. So for example, suppose we had a math error, and so now this is our exception object. We'll call it ME for math error. We write some code and we handle any math problem that is happening. And then when we're done, we decide we don't want to return to the code where the exception occurred. We'd like to rethrow it back at the stack so the stack can further handle the problem. So we just take the object and say throw, which basically is telling the operating system to take that object and rethrow it into what's left of the stack. We can also decide to create a new, different type of exception and throw that at the exception stack. So, for example, if we're running some code and then we hit a math error, and this is the code that catches it, the math exception object is ME. We catch that and then we say if ME is a divide by 0 exception, then we'll throw a divide by 0 exception. So again, this really doesn't do anything different. It's saying if it's a divide by 0, I'm going to throw it, I'm going to create a new divide by 0 and throw that one. Okay. So now here's, I guess, another interesting design question. If you have a method A, which calls, so suppose method A wants to handle, so you write try code, you say try, in try you call method A. And then you catch, let's say, an IO error. Method A calls method B, and method B has a handler for IO methods. For IO exceptions. Method B calls method C. Method C also has its own way of handling IO exceptions. File not found type exceptions. So if A calls B and B calls C and C hits an exception, which of them should handle it? that, let's say for example, well, here, okay, let's say we have a function FUNC, func, and then we have GUNC, junk, and hunk. If HUNC calls FUNC, and FUNC has a problem, but HUNC handles the problem, but FUNC also handles the problem, should they both handle it, or which one should handle it? So if this, yeah, if this was a, you're
You
designing,
said
yeah,
the problem was in FUNC, in func.
yeah,
The problem's in func and hunk solves func's problem.
handles them. So in other words, whenever we say try from here to here, you're saying if an error occurs in this code, I can anticipate this coming, so I'd like to handle it. But suppose this code also handles it. Should they both handle it? So should the handler from this one handle it and then come back to here and have this one also handle it? Or should the person who wrote this method, it's their responsibility to handle it? Or would you allow the flexibility that the person who wrote this code could tell you that this problem may occur, so kind of advising you, you better handle it? Or how would you design that?
Would it take more steps for hunk to catch the problem in func than for func to catch its own problem?
Right, so for example, if, yeah, so this is kind of an interesting design discussion. If FUNC handles it, and HUNC also handles the same problem, should it be handled twice? Should FUNC handle, well, here's the thing, if FUNC handles it and doesn't throw it back at the stack, if it just handles it and keeps going, then HUNC might not even know what happened. And is that a good thing? Because HUNC wants to handle it if it happens. So if FUNC can mask it by solving it, by putting stuff higher on the stack of exceptions, handle it, and then HUNC may not even know it happened. So should we add something to the language that tells HUNC that FUNC hit this problem and I'd like to pass it to HUNC to let HUNC handle it? So, I don't know, do you think that's a good design thing, or is it adding too much confusion?
Seems like double work.
Yeah, it seems like it's redundant almost. Just gonna be adding
That-
on to the same thing.
Well, so let's suppose this top function opens up some file, and the file may not be there. So should this thing handle the file not found, or should it say, anybody who wants to call me, I want you to know I may have a file not found exception, and you might want to handle that. Or should we let that, because maybe who's ever calling it handles it differently.
I feel like if the problem can be solved in the first one, you shouldn't let anyone, too many people touch it.
Right, so let's say for example, yeah, like I was saying, if this thing opens up a file and the file may not be there, should we make this file opening function handle all file not found errors? Or should we allow methods that call it to handle it the way they want to? Because they may all handle it differently. Some may say, oh, if the file's not there, terminate me. Other ones may say, oh, if the file's not there, I have a backup file. I can handle it. But this function may not know how the caller wants to handle it. So we might want to add a mechanism that says, I'm going to be opening files, which means file not found is a very likely problem. I want to warn you, you better handle it. Something like that. So anyway, so there's a throws keyword in Java. You could say a function, DUNC, throws this exception. I'm going to be opening files and closing files and saving files, and stuff may be going wrong. If you want to use me, this is something that you better handle. To tell you, you know. So it's just a way of saying, this is stuff that could go wrong, and I throw, and you can actually make a list of them, you can say comma and list out, you can list out all the exceptions that this thing may throw. And then someone who's using it would then know to try to catch those exceptions. So yeah, just one more feature added. So it's again, it's a design thing that Java would like you to be able to know. So you could create a method for others to use. You know your method may have these problems, but rather than catch them and handle them, you're just telling anyone who may use your code, you might want to handle these problems. So it's kind of like a warning list when you say throws and you list out all the exceptions that you throw. And then one thing Java added that C++ didn't have, at the end of your catch blocks, you can have a block called finally, which will always run after a try block runs, whether or not there's an exception. So, for example, if you have code that opens up a file, so opening up a file means you have exclusive access to it, nobody else can use it until you're done. Then in your try code, you're doing some stuff with the file. You may hit a problem, you may not hit a problem, you may hit an exception. Maybe you do, maybe you don't. And then when you're finally done with it, you want to close the file, save it away so that way someone else can have it. So what Java does is it has a finally block, which will run whether the try code runs successfully or the try code does not run successfully. So here's an example. Here's kind of like where we're taking a lot of stuff we learned this semester and putting it all into one example. So we have a list generic of integers. So I'm making a list of an array of integers. And then I'm opening up a file, some file.txt, which is going to be a list of integers. And then I'm going to read through those list of integers and write them into an array. So since stuff may go wrong, I may want to, as I'm reading from the file, I may want to put in a try block. I may want to say try, reading from a buffer, take the string that's coming in, make it a null. As long as it's not null, keep reading a new line, and keep adding what I've read to the integers. Now at this point I'm not going to say, now that I'm done, I'm going to save the file away because something may go wrong in the process. I may have a file not found error, which I need to help, which I need to handle. And maybe I want to print out the stack trace. If I don't have a file not found, maybe I have an I/O exception, which is a more vague version of, maybe I went to write something to a file and I had some kind of an I/O exception. And then I have a final block called finally, which basically says I want to close the file. I'm actually putting a try and a catch in that. And as I go to close the file, I go to save it, I can't save it. Maybe I made the file so big I can't save it, there's no more disk space. So I could hit an exception trying to save the file. And then if that's the case, I'll catch an I/O exception and maybe handle that too. So yeah, the one thing that Java added that C++ doesn't have, within the try, followed by a series of catches, the catches are all exception handlers you're stacking up on top of the stack that the operating system has already. And then we have a finally block, which will run whether or not this code ran successfully or ran and there were exceptions happening. In either case, this code will run. The finally code will run. So you can be guaranteed that this code will run. You might think, well, why don't we just put it outside of the try and the catches? Well, if any exception hit, then this code wouldn't run. And then having it in a finally block lets it run whether this code ran successfully or an exception had occurred. What was done in C++ was they have a thing called catch, open paren with 3 dots, dot, 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 close paren, which means it will catch any exception. And if you hit any exception above this last block you wanted to do, you would always want to throw it to dot, 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 and then put whatever finally code you had. So they kind of just removed that and replaced it with the finally section. So it's popular Java, Java interview question, what is final and what is finally, two totally different things. Final means like variables that can't be overwritten or methods that can't be overwritten. And finally is the code that will always run. Finally always is associated with the try block, and it's the code that will always run, regardless of whether the exception hit or not. Okay, and then we talked earlier in the semester about threads. So here's an interesting thing. Suppose you have a piece of code that has children threads, and one of the threads hits an exception. One of your threads maybe does a divide by zero, but the other threads do not do something like a divide by zero. Should the exception kill the parent and all its children, or should the exception just kill the thread that had the exception? So if the idea of what's called being thread safe, when we're saying exceptions are thread safe, it basically means if there's a child thread that hits an exception, whether you handled it correctly or not, or you wanted it to be terminated, only the child that had the exception would get terminated, the other children would keep running.